All right. I'm very happy to introduce our next speaker. Helen Oleynikova is a senior software engineer at Nvidia in Zurich and previously did her PhD at the Autonomous Systems Lab at ETH Zürich and did there, during the PhD, did some pioneering research in dense mapping and path planning for flying robots, and previously worked with me at Microsoft. And so I'm happy to have to hear this presentation from work from NVIDIA.
Thank you so much, Jeff. So it's my great pleasure to talk about some of the work and kind of my opinions on 3D robotic perception and how it interacts with mixed and virtual reality and augmented reality as well. So first, just a little bit about me. So as Jeff mentioned, I'm currently at NVIDIA. I'm part of the Isaac 3D perception team. So we're focusing mostly on 3D perception on board a robot. And previously I worked with Jeff working on robotics and mixed reality at Microsoft, did mapping and planning before, and had a couple of other jobs. But what's kind of the big picture summary of this talk is that I really believe that 3D perception is an essential tool for human-robot collaboration in augmented reality, mixed reality, and virtual reality, and probably outside and real reality as well. And so the outline of this talk is, first I'll talk a little bit about spatial representations in both robotics and XR. I'll discuss a little bit in more detail about volumetric mapping, which is my favorite topic. And then I'll introduce NVBlocks, which is what my team has been working on for the last year, and show some applications to what I've discussed. So first, let's take a big picture, a big step back, and let's talk about how robots view the world. So here I have some examples of, one second. Here I have some, here we go. Yeah, here I have some examples of RGBD image. Wow, this is huge lag. Great. Of RGBD imagery. So this is an RGB image. This is a depth image, and this is an IR image. So this is from the real sense. This is kind of a common sensor setup that most robots will have. So this is fairly similar to how you view the world. And down below is a view of what 3D LiDAR sees. This is much more accurate than how you see the world, but also kind of a different spatial, kind of gives you different information. It's much more sparse than a camera. But also can see, accurate depth to hundreds of meters out. And then so the task of robots is to take these disparate sensors and tens of other sensors and combine them into a spatial representation that they can actually use to act in their environment. So there's a lot of different types of maps that you can build out of all of this data. To start with, there's different densities. So we can talk about sparse maps. So this is like this one here. So this is a feature key point map. So this is only kind of storing corners in an image. There's semi-dense maps, which have corners and edges and a little bit more. And then there's dense volumetric maps, which basically try to capture the entire volume of obstacles where they are and aren't. And all of these maps are useful in certain contexts, and every type of space representation or map has its own purpose. So, sorry? Okay, great. Sorry, so all of these maps have different purposes. So some can be used for localization and localization alone. Others are used for path planning and navigation. Also object tracking requires different types of map representations. And finally, I think the kind of the richest information that a robot can have about its environment is semantic information. So room labels, for example, Jeremy's office, Nick's office. The information about where walls and doors and floors are. The topology of the space, and for example, also object detections of important objects like the milk fridge or the coffee machine for important tasks like fetching me a coffee. And luckily for us, a lot of these map representations and kind of 3D perception capabilities that robots need to have overlap heavily with what needs to be done for effective VR, AR, and MR systems. So I think most of the systems kind of used today actually have a very common 3D perception setup. So most use a sparse feature tracker for estimating the pose of a headset or a phone, and then a dense mapping system of some sort for generating collisions and occlusions and giving you a kind of a 3D sense of the world. So on the HoloLens 2, this is done exactly as I've described. There's cameras on the front that kind of track the position of the headset. And then there's also the same sensors on the Azure Connect that gives you dense information about the world. And here you can see a spatial mesh of the environment. Even on the Oculus Quest 2, there's a very similar system. So again, the pose of the headset in the space is tracked using cameras without having to use external sensing, which was the cool innovation of the Quest. But there's also, from the camera images, they also do some stereo, some multi-view stereo, and they're able to get a rough 3D map of your room and your environment, and preferably keep you from punching the TV as you're playing the game. So even there, in this kind of constrained environment, this 3D information has a lot of use. And then finally, in ARKit, ARCore, and so on and so forth, a very similar system is used, mostly cameras for tracking. Then on the iPhone, on the recent iPhones, there's actually a LiDAR sensor, so you can have really high fidelity 3D reconstructions of your environment like this. On other phones, you just have cameras, and you usually end up with worse quality depth maps, but you still, in order to render realistic AR occlusions, you really need the dense depth information about the world. And so kind of transitioning, why do I think it's important to combine XR and MR and AR and VR and so on with robotics? So if we look at commercial mobile robots today, most of the ones that are actually deployed do logistics. They move things from point A to point B in a warehouse that's usually fairly tightly controlled. And there's very, very limited human interactions. Mostly the humans should stay out of the robot's way, and vice versa. And I think that's really not the future, right? The future I would like to see is a future where robots can navigate, operate in much more complex environments, have more complex interactions with their environments, and maybe they can help out on construction sites and disaster relief scenarios and so on. But unfortunately, these scenarios are all really hard to do full autonomy, and to be useful in most of these scenarios, robots need to be 99.99995% reliable. And if you look around at the works you'll see at IROS over this week, we'll probably can all agree that we're not 99.9995% reliable on these scenarios yet. So I think a key to enabling these scenarios for robots to be useful is actually teleoperation. And I think we can all agree in this room that teleoperation through VR, AR, and MR is a really promising field where I think we can really allow humans to interact with robots in a much more natural way and help them out through tough scenarios in a much more natural way. And the other thing I'm really interested in is not, this kind of warehouse scenario where the humans go to this part of the warehouse and the robots go to this part of the warehouse and hopefully never meet, but actually having humans and robots work together in a shared space to complete tasks, similar to what they tried to do with Baxter, but really collaborating in a shared space rather than just staying separated. And of course, as you've seen from all the talks today, mixed reality, augmented reality is really, really key to kind of giving you a lot more insight into what the robot is doing, giving you a more natural way to interact. Back to kind of the key point of the talk, is that I think sharing a common spatial representation is going to be key to both sharing spaces and interacting with robots, and also in teleop. It's really important to let the user, the operator, see what the robot is seeing and give them kind of a natural way to interact with their environment, even if they're embodied as a robot. So I'll show a little bit of work that Jeff and I did together at Microsoft. I'm sorry, Nvidia, that I think motivates us fairly well. So here we went to a search and rescue training ground, and we have this robot. It has a LiDAR on it, and we have a HoloLens 2. And we'd like to be able to interact with a robot in a new environment. So with this setup, what this involved was me nodding my head a lot and reconstructing a 3D mesh of the environment with the HoloLens. So you can see that overlaid here. And then to get this to a spatial representation that the robot can localize in and then use for collision avoidance, we then had to slice this mesh into a 2D map and then send that over to the robot and give it a prior pose in this. And then that's how we were able to like achieve co-localization with the robot. So the robot is using a 2D slice, the HoloLens is using a full 3D mesh and visual features. And the dream would be really to like have both the robot and the HoloLens do the same thing, talk the same language, and both kind of share a single representation of the space. So kind of to bring this to the next part of the talk. So in terms of having shared spatial representations, I think volumetric mapping is really, in getting volumetric mapping right and in a way that's shared between AR, VR, MR, XR, whatever, and robots is going to really unlock a lot of capabilities, both in teleoperation and shared space. And so the next part, I'll focus on volumetric mapping approaches. So why volumetric mapping? What is volumetric mapping? So volumetric mapping is basically a class of mapping methods where you represent the volume of the space. So both what's inside obstacles and what's outside. And the key part of this is that this is a dense mapping approach. So you can kind of query any point in space and have information about whether it's in collision, out of collision. And it's already, a lot of these methods are already widely used for collision checking, for path planning for robots. It's quite easy and fast to build these representations. And then you can also get gradients, and this is super nice for path planning. And it's also kind of the same methods, and it's the same questions that you need to answer for rendering an AR image, like is Pikachu in front or behind the desk? And to do that, you need to have some volumetric information about the scene. So we're really using the same techniques already in both. And for teleoperation scenarios or scenarios where you're not sharing a common space, you can also easily build a mesh and maybe color it to give the operator a really nice view of the environment. So again, to reiterate a little bit, here's the Pikachu scenario. In order to render a realistic AR experience, you really need Pikachu on the correct side of the leg, otherwise it looks fake. For robotics, I think for teleop, it's really important to like stream the full understanding of the robot's environment to the operator, not just the current image that it sees, and also to allow the robot to plan autonomously. And if we share spaces with robots, then like dense maps can be used to co-localize robots and operators. You can render occlusions. You can kind of use the same information to like communicate with the user as the robot is using for planning. And I'll talk a little bit about like the requirements on these volumetric maps if we intend to use them for teleoperation, because I think they're a little bit more strict than for other scenarios. So the maps need to be built on board the robot. They need to be built quickly and with low latency from the sensor input as the robot is exploring a new space or to communicate any dynamics in the environment. They need to be transmitted really efficiently to the operator. I think this is one key thing, is if you're streaming, like, you know, if you have 6 cameras on your robot and you're streaming 6 cameras live, you're going to run into some of the latency issues that we've seen in other talks. And to send only updated information, and it needs to be kind of readable to the user. And what you can see on the right-hand side here is just a grayscale reconstruction of a robot flying around this earthquake damaged environment. And if you compare kind of what you can see in just one live image of what the robot sees versus kind of the context you get about the scene from seeing this reconstructed view, which is much more of an off-board view, I think we can agree that there are certainly scenarios where just seeing what the robot is seeing right now without the context, it's much harder to do the correct thing. So to transition to what I'm trying to sell to you guys. So what my team has been working on for the last year or so at Nvidia is called NVBlocks, which is a fast 3D volumetric mapping library for embedded devices. Embedded here meaning still has a GPU, so ARM64, Jetson, and so on. And the way it works is you feed in either a depth image or a LiDAR point cloud or both, whatever your robot has attached to it, and the pose. So the pose needs to be computed separately. You run NVBlocks on it, and then you get a mesh, a truncated signed distance field, and a complete distance field that can be used for collision checking. And this requires either an x86 computer and a GPU, Nvidia GPU, needs to run CUDA, or a Jetson or another ARM64 computer with a Nvidia GPU. And so I'll very quickly go over how this works. So this is an example of building, one of these meshes, which I think you can agree gives some context at least about the environment the robot is in. This is in our office in Zurich. So this is just a ground robot driving around. This is all being built live on board and streamed to my desktop as I'm driving it around from my desk. And so the way you build the surface representation, if you guys are familiar with mapping, it's a very standard truncated signed distance field. The idea is you take basically a depth image and you try to build a voxel grid of a moving average of distances. So you integrate some distances close to the surface in front of the surface and some distances behind. And then as you integrate a lot of images together, you're able to overcome errors in the individual depth map. And we have optimized this a lot for the Jetson. So it takes only 0.3 milliseconds to fuse a full depth frame into our framework on a desktop and 1.6 milliseconds on a Jetson. And then you can get a mesh directly out of this representation using marching cubes. And so the other cool thing that our library does is also build a full signed distance field, the Euclidean signed distance field, which basically for every point in the space is a distance to the nearest surface. This is maybe a little bit less relevant for XR, but it's super nice for path planning because you can just get your collision costs directly. You can get collision gradients directly. You get basically a direction vector to the nearest obstacle. For any query. So this is quite a powerful map representation for a lot of robotics applications. And we do this really fast incrementally on the GPU as well. So this is some novel method that we'll hopefully publish soon. And I'm not quite as efficient at the ESDF computation on the Jetson. So it's 1.8 milliseconds on the 3090 and 11 milliseconds on the Jetson, but I'll try to bring that down as well. But basically this comes down to 5.5 milliseconds on per frame on a standard desktop and 26 milliseconds per frame on a Jetson. You're able to basically have the kind of representations I showed before. So you get a mesh, you get a distance field you can use for path planning. You know which parts of the mesh have been updated, so you can stream that directly to an operator. And I think it's kind of hopefully a really powerful representation to use for a variety of applications, including XR. And when we compare it against my PhD work, which is very similar, but just on the CPU, we achieve 220 times faster on the TSDF, 110 times faster on the ESDF, and mesh is 4.5 times faster, which is all right, I guess. But so yeah, this really brings it up 2 orders of magnitude to being able to make higher resolution maps, being able to map larger spaces, being able to kind of integrate more sensors into it. And then I'll just very quickly go through some examples of how we've used this. So the first is to just show how this can be used for 2D navigation on a robot. So we have a ground robot, and here we're actually computing a 2D signed distance field that's then being used by a standard navigation stack from ROS. Here we kind of show an example of this in simulation. So the robot is driving around and reconstructing a mesh live. Here, the brightly colored stuff is the collision cost that's being overlaid, and that's being used for autonomous path planning. This, of course, also works in real life. So you see kind of the same view here. The robot is driving around, reconstructing a live mesh of its environment. This is done 100% entirely on board, everything live, and also gets collision costs that can be then used to avoid obstacles in unseen space. That's kind of cool, but you can do that with really basically anything. I think another really cool application in robotics is this was a work that was done in collaboration with the research team at Nvidia on basically using NV blocks to directly compute collision costs in a 3D map, and then being able to use that for robot arm motion planning on the GPU. And so the cool thing is, because all of the data stored in the GPU, we can do millions of queries in a matter of milliseconds. So we're able to really plan and evaluate a lot of different paths, allowing the robot arm to plan in in frequently challenging environments and evaluate a lot of different possible plans in a short time. So the other thing we talked about is being able to store semantic information in in a map representation that robots really need to know semantics. So this is some kind of some early work we're doing on basically splitting the map into different semantic layers. So here we're taking human segmentation results. Here, this is from ground truth. And instead of fusing them into the 3D mesh, we're actually fusing them into a separate layer that's kind of dynamic obstacles. So now we know exactly where in the scene the humans are. We don't integrate we can treat them separately for both collision computations and for interaction and other scenarios. So this is work that I'm really excited to continue to see how we can integrate more semantic information. And finally, the actual meat. So this is actually work done by iBotics in the Robotic Systems Lab at ETH Zürich. So the idea here is this is a remote VR teleoperation of the animal robot. And the idea is that the operator is sitting quite far away, so there's some significant latency, but it's still able to teleoperate this robot down the stairs and to the closet. And we'll see in a second kind of what the operator sees. And I think this is really motivating work for why I think 3D reconstruction is important. So as you can see, it's streaming the image directly. And there's quite a lot of jitter. The robot is shaking as it walks up and down, and it's a little bit, I would say, hard for the operator to focus, whereas we can anchor that in like a 3D reconstruction of the rest of the scene that's being shown here, which both gives the operator kind of spatial context on what it can't see in the current scene, and also it's just a little bit easier when not the whole environment is shaking. We can stabilize that a little bit better. This is all available online and for free under permissive licenses, so feel free to download it and check it out. I'd love to get your feedback. And so in summary, I'll be very short. I think sharing a common spatial representation between robots and XR devices is important. I think volumetric maps are really cool for both. And I've tried to sell you NV blocks, which is for free, which can run on Jetson and GPU to do volumetric mapping really quickly. And we've shown some examples of those. So with that, thank you very much.
I think in the interest of time, we should probably save any questions for the panel discussion, but let's thank our speaker again.